Hello everyone, this is Attila. So on our last video we were able to finish the introduction and set up our environment variables. On this video we will be more focused on developing the actual code for our GPT model. So if you're ready, let's get started. So let's go ahead and get started. The first thing we need to do is open the IDE that we're going to use. You can use any IDE like VS Code, Visual Studio, and etc. I will leave a link for VS Code in the description below if you need to install it. And so first of all, we need to add our imports into our program so we can later use the functions included in the libraries that we import. So let's go ahead and import OS, math, artparse, JSON, and random. These are the basic Python helpers that we'll be using. And later we'll do from data classes, import data class, and to easily configure the objects that we'll be using. And from typing, import optional. This will be later used for the optional values that we'll need to use in our code, and I'll be explaining it later on as we progress further into the code. Then we'll import the NumPy as np, import torch, import the torch.nn as nn. Then we'll be importing torch.nn.functional as f. So after this, we'll be importing from torch.utils.data, import dataset and data loader. Then we'll be importing sentence piece, import sentence piece as SPM, and from QKDM, import QKDM. So these are the basic libraries that we need to import, so that we will be making use of all of these in our code later on. So for example, import NumPy we'll be using for the number crunching. Then for example, QKDM we'll be using for the progress bar when we are training our model. And sentence piece, for example, we'll use it for tokenizing our data, and etc. And we'll be seeing all the functions, all the use cases of all these imports later on in the code. So now we can go ahead and start by getting our utility to pick up either if it's the machine that we're using is either using a CPU or a GPU. So what we can do here is define get device, return torch.device, and we'll use sudo if torch.sudo is available, it will return true, else if it's false, return CPU. Okay, and so this is just the basic that we need to do, so whenever our model is running, it can quickly identify whether we're running on a CPU or a GPU. And now we can go ahead and make the tokenizer, which will train our model on the Shakespeare text. Like this tokenizer will turn the words and characters actually into numbers. So let's go ahead and define train sentence piece from earlier. Sentence piece. Then with the parameters will be input txt, string, model, prefix, tokenizer /sp. Then we'll also choose the size of vocabulary for the model. This can be any size, but for this tutorial we'll be using just 8,000 characters. Yeah, so now that we have defined the parameters, we can go ahead and make os.make directories, os.path.directory name, model prefix. And if it exists, equals true. Then we'll put the SPM sentence piece dot sentence piece trainer dot train. And we'll put input equals input txt, model prefix equals vocabulary size, character coverage equals 1. So this will basically mean that it will cover all the characters that we have given it. Model type equals BPE. This is the byte pair encoding model, and this is usually the most common method used in GPT models. Then we'll use pad ID equals 0, Onc ID equals 1, boss ID equals 2, EOS ID equals 3. With that, we should be done with the sentence piece, and now we should have to print that we were able to train the model. So we'll do print f, we write OK, trained sentence piece at model prefix dot model. So basically, once we're done with training the model, we should be able to get this print in the command prompt, and this will show us whether the operation was successful or not. So now that we're done with that, we can start focusing on making the wrapper, like adding some more features to the sentence piece tokenizer, like encoding and decoding. So we'll make the class for it first of all, class sp tokenizer, define init self model path str. Then we use self.sp equals spm sentence piece dot sentence piece processor. And then we'll use self.sp load the model path. Then we'll use at property and define. Here we'll start to add the features of the tokenizer. Define vocabulary size self, return self.sp.get pieces size. This will, when we run this function, it will give us back how many tokens there are in the vocabulary or the dataset that we are provided. And then we'll use the define encode function for self text str, return self.sp encode as IDs. Bring that down. Encode as IDs, and the parameter we'll give it is the text. Okay. So what this will do is, when we give the model a text, it will be able to convert it from strings and characters into numbers. Here we call them IDs. We call these numbers as IDs. And it will give us the list of these IDs. And now we will use a decode function to make the reverse of the encode function. So define decode self. Here we will give it IDs as the parameter. Return self.sp.decode IDs. And the parameters we'll give it is list, the list of maps containing integers and IDs. So what this will do is, the IDs that we had from the text, now we'll be able to reverse this operation, and we'll be able to convert IDs back into text now. And this is how the decode function will be done. So just to give you guys a quick recap of where we are so far, we have made the tokenizer. Basically what this tokenizer will do is train a token with sentence piece. All right, we'll train the GPT model to tokenize with sentence piece. It will learn from a small vocabulary from our Shakespeare text. Then this text will turn the token into IDs that the model will be able to understand. Okay. So vocabulary size controls how many pieces that we can learn. So, and as I said before, we'll also use the BPE model, which is the most common method. And then we will use the tokenizer, the class here we have put. Basically this class has two functions, two main functions. It's encode and decode. Encode will turn the text into IDs, and decode will turn the IDs back into texts. We will use basically this function everywhere. So now that we have understood the functions that we have created so far, we can now move on to the next part. Here, for the next part, we have to make a preprocessor text, which turns the text into token IDs. We will load the raw text, encode it to IDs with our tokenizer, then split it into training, and then we'll validate it. And then finally, we will save it to a compressed file so it's able to load faster. So let's make it. We'll use define preprocess text, preprocessor text to IDs. Then we'll put as our parameters input txt str sp model str output npz str, and after str we should put value frac float. Hold on, let me scroll over. Float 0.1. So now inside this function we'll write tokenizer sp tokenizer using the sp model. With open input txt or encoding equals, we'll set it to UTF-8, the most common method. UTF-8 as f. Text equals f.read. So basically what this will do is it will load the raw text that we provided for the model. Then we will convert IDs equal mp.array, and we'll use tokenizer.encode text. Dtype equals mp.integer. We'll use 32 bits. So yes, this function will be able to convert the text into the token IDs, as I mentioned earlier. Okay. So we'll use the number as len IDs, the length of the IDs. This will be n. So basically the IDs are the numbers I mentioned earlier. So n will just show their size, pretty much. Nval equals integer n multiplied by value fraction. So basically, it will split 10% of the text for validation. So it will, for the prediction, this is important that we split 10% of the text. Then train IDs equal IDs. And we'll use IDs, sorry, n val. Then we'll use val IDs. Yes, here we'll use minus and val. Now we will make the OS directory. So basically we'll put os dot make directories, os dot path dot directory name, output out mpz. If it exists, return true. And this will basically make the directory for the OS path. And now we have to save this. So we'll put mp saves compressed out mpz train equals train IDs, val equals val IDs. Basically, this function will now save the data, even compressed version, and the model will later be able to use this data. Now that we have written the function, we need to return the print that the function was successful, or the operation was successful. So we'll put print f, okay, saved token IDs to out bz, or train equals we'll put length train IDs, then we'll also put the value of the length of the IDs. We'll put val equals length sorry, we have to put like this, value equals length val IDs. Now that we have put them, we'll now make the vocab vocab equals talk.vocab size. Let me hover over to this side. Yes, vocab equals talk.vocab size. So now this should be the success message that the operation has been successfully completed, and we have saved the data and turned the full text into train and validation sets. And next we will make the configuration class that holds all the model settings. Like we'll put the model, for example, which will be the size of the vector that represents each token. Number of heads is like how many parallel attention heads we'll use, like which will let the model focus on different parts of the context at once. Then we'll also have layers, which will show how many transformer blocks we stack on top of each other. Then the block size is how far back the model can look at once, like the memory, how many things it can remember at once. It's like a memory window. So let's go ahead and make it. First, we have to call the data class GPT config, the settings I said earlier. Vocab size int the model int equals 256, number of heads equals 4. This can be actually based on your preferences. Like we'll make a simple model right now, so the overload is not too much. However, these numbers can also actually be changed according to your specific needs. And layers, number of layers integer equals 4. So this is the model is the embedding and the hidden size. The number of heads is the number of, like as I said earlier, the attention heads, and the layers is the transformer blocks. EFF int equals 0 to 4. Block size 256 for the max context length, and we'll say dropout float 0.1. This is basically how much we want to cut from each text. So we'll put 10%. Class. Now we'll make the next class, which will be the self-attention class. And basically this is the attention layer of the GPT model, the main part of the GPT model. The idea is that every token looks back at previous tokens, and it will decide which ones are important for predicting the next word. So we'll split each input into 3 versions: the queries, the keys, and the values. Queries will be like, what am I looking for? Keys will say, what information do I carry? And values are the actual information passed along. So then after we have given these 3 queries, keys, and values, the model calculates similarity scores between each query and keys, and then it will decide which one to give more attention to. After this, it will combine all the values according to the attention weights that it was given. So basically, the causal mask will also make, which is important, it blocks tokens from looking into the future. That way, when we're predicting, like for example, the number 10, it can only use the numbers 1 through 9, not 11 or 12. This is where we will use also a causal mask. So let's go ahead and make it. We'll use class causal self-attention. We'll say nn.module nn.module. We'll give the define init self config GPT config. super dot init assert the model. Then we'll use number of heads 0. The remainder should be 0. Then we'll use self the model equals the model self dot number of heads equals number of heads self dot head dim equals the model divided by n heads. So for this assert the model, we'll make sure there's an even split between each head. Then we'll put self dot qkv equals nn dot linear the model 3 times the model. So here this will like project the tokens to Q, K, and V. Like it will be queries, keys, and values. That's basically what QKV means. Then we'll make self.out equals n.linear the model. This will be the output projection. Then we use self dot attention drop equals nn dot dropout from earlier. Dropout self dot resit drop equals nn dot dropout nn dot dropout. Then we'll put dropout as the parameter again. Now self dot register buffer. This is the mask we'll put. Mask we'll say torch trill torch ones 4096 4096 unsqueeze 0 dot unsqueeze 0. So basically this would be the casual mask buffer, and now we'll just register the buffer, basically just implement the mask. Now we will have to define, one second. Now we'll have to define the forward self x c. We'll give the shape of the x dot size queries keys and values equals self dot queries keys and values of x. Now queries keys and values, we'll make them equal to qkv dot split self d model dim equals 2 q equals q dot view b t and self dot number of heads self dot head dim. Then we use the transpose 1 and 2. Then we're just making the vector here. Q equals k equals k dot view b t self dot number of heads self dot number of heads self dot head dimension, and we'll use the transpose again of 1 and 2. Now we make the values dot view b t self dot number of heads. We'll use self dot head dimension, and once again the transpose. Oh, the transpose of 1 and 2. So now that we have this, yes, so now that we have the transpose of the QKV and written down, we should now make the attention. K dot transpose divided by math dot square root. We have to use this from the library. Square root of self, head, and dimension. Now attention dot masked fill self dot mask we'll put t and we'll put make it equal to 0, float, let's say infinite. Mine is infinite actually. Then we'll put the attention self dot attention equals self dot softmax. In the parameters we'll put attention and dimension equals to -1. Then attention finally we'll put self dot attention drop attention. Now we'll put the y, which will be equal to attention at the value y equals y dot transpose 1 2 dot contiguous view dot view of b t and c. Y equals self dot resid drop self dot out y, and now we'll return y. So now that once we have finished the casual self attention class, as I said earlier, now the token will be able to see the queries, keys, and values. It will be able to mask which values to avoid, and it will also be able to determine which values hold stronger importance. Alright, so that's where we'll stop off for today. So far in this video, we built a tokenizer that will convert the text into tokens. We built the main data pipeline that will feed these tokens into the GPT. And we built the most important part, the causal self-attention layer. This part will help the GPT decide which tokens to pay attention to when predicting the next token. In the next video, we'll go ahead and finish our code and even be able to test our GPT model. And if you're following along, make sure to save your progress as well and go over line by line again through the causal attention layer code, because that part is the most trickiest part, but it's also the most important and most powerful part to understand when building a GPT model. Thanks for watching, and I'll see you in the next one where we'll finish our GPT model together.